We want to start this section by looking at the oxidation of aldehydes. Now, we know that we can oxidize aldehydes using some of the chromic acid variations that we saw back in chapter 12, where we take either chromium 6 oxide and put it in sulfuric acid, or the sodium or potassium dichromate, put that in sulfuric acid. We know that those will oxidize aldehydes to form carboxylic acids. We also, under the right conditions, can use potassium permanganate, which is significantly less toxic way of doing the same thing. But we have another way of oxidizing aldehydes that is actually quite clever, and it will oxidize aldehydes but leave other functional groups like alcohols alone. And so that is going to be the Tollen's reagent. And it's simply where we use silver 1 oxide in ammonium hydroxide solution, aqueous ammonium hydroxide solution. What's cool about this is that here we've got an aldehyde that we can oxidize with the silver 1 oxide and the ammonium hydroxide solution, and it will oxidize that aldehyde to the carboxylic acid, but it will leave the secondary alcohol alone. It'll leave all your alcohols alone. It'll only oxidize the aldehydes, which that is pretty cool. And on top of that, when you do this reaction, with the silver 1 oxide, you will deposit metallic silver on the inside of your reaction flask. And so you'll end up getting a silver mirror on the inside of your flask. So if you go to YouTube and search Tollen's reagent, and you'll see this, you can go observe this. So, all right, let's look at number 15 on the in-class assignment. Since the ketones don't have the hydrogen on the carbonyl, they do not undergo this. So we don't oxidize ketones, we don't oxidize alcohols, we only oxidize the aldehydes. Pretty cool. So let's go to number 15 on our in-class assignment. I'll switch over here. All right, so we've got this compound, and I've taken the liberty of redrawing it where we can see the carbonyl here, the aldehyde here. And we're going to treat each of these with these different reagents. And some of this is going to require that you go back and review. And I'm going to encourage you to go back and review all these things anyway, not just for this problem, but before you take a test, before you go on to the next section, because all these things like sodium borohydride, lithium aluminum hydride, we're going to use those not only in this chapter, but in chapters 18, 19, 20, 21, and going on and forward, we're going to use them in synthesis problems. So you'll want to know how to use these. Sodium borohydride is a reducing agent. Well, we can't really reduce this alcohol without going crazy with it. So we can't reduce those, but we can reduce this aldehyde to an alcohol. So when we do that reduction, this alcohol will remain the same. All right, but this will get reduced to an alcohol, and that secondary alcohol will remain the same. So sodium borohydride will reduce the aldehyde to a primary alcohol, and it won't affect the other functional groups. And in fact, the lithium aluminum hydride will also give you that same reagent. So lithium aluminum hydride will also reduce the aldehyde. So I'm not going to draw that product out again. It's the same product. Now for this one, pyridinium chlorochromate. What will PCC do? Well, remember, pyridinium chlorochromate is a mild oxidizing agent. It will oxidize this primary alcohol to an aldehyde. It'll oxidize this secondary alcohol to a ketone, and it will not affect this aldehyde. So we'll get an aldehyde there. This aldehyde will remain unaffected, and that secondary alcohol will get converted into a ketone. All right, now this is the one we just looked at on the presentation just a minute ago. I'll go back to it just for a second. This is the Tollen's reagent, and it will oxidize the aldehyde to a carboxylic acid, but it'll leave these alcohols alone. So unaffected primary alcohol. All right, unaffected secondary alcohol. But then this aldehyde will get converted, this aldehyde will get converted into a carboxylic acid. All right, finally, we've got chromium 6 oxide, sulfuric acid, and water. This is essentially chromic acid. This is a very strong oxidizing agent. It will oxidize our primary alcohol to a carboxylic acid. It'll oxidize this secondary alcohol to a ketone, and it'll oxidize the aldehyde to a carboxylic acid. So we get the carboxylic acid there, ketone here, and carboxylic acid there. So you can see this gives us a lot of options as to, do we want to selectively oxidize something, or what exactly do we want to do? So pretty handy set of reagents there. All right, well, now we want to look at organometallic reagents, and these are compounds where we have a direct covalent bond between carbon and a metal. And the metals that are most commonly used are going to be lithium, magnesium, and copper. However, there are some other options. We're going to focus on these in this chapter, but there are some other options, including some nonmetals here that we'll talk about at a later point. But here, we've got a covalent bond. And when I say it's a covalent bond, it is definitely a covalent bond, but it's a very polar covalent bond. And we'll talk about that here in just a moment. So we've got that carbon-metal bond. And again, lithium, magnesium, and copper are the ones we're going to talk about in this chapter. It is possible to do reagents that include tin, silicon, thallium, which sounds pretty dreadful. Thallium is dreadfully poisonous. Aluminum, titanium, mercury. So there are lots of options that are available. But like I said, in this chapter, we're focusing on these three metals and these three types of reagents. So the types of reagents that we're going to be discussing are organolithium reagents, the organomagnesium reagents, or sometimes we refer to these as the Grignard reagents after the discoverer of these reagents, and then organocopper reagents, which we will often refer to as organocuprates. We're going to find that the more polar these are, the stronger they are as a reagent. And we'll find these first two are quite reactive. And the third one, while it's quite reactive, it's not quite as reactive as these two. So how reactive are these? And as I mentioned on that previous page, the more polar the carbon-metal bond is, the more reactive the organometallic reagent is. So we'll find that the organolithium and the organomagnesium reagents are very reactive because they're quite polar. And that the organocuprates are somewhat less reactive because they are somewhat less polar. So, and this is an important point. When we're using the organocuprates, only one of the R groups ends up getting used as a nucleophile. The other R group is lost in that process. So in these organometallic reagents, as I mentioned, they are covalent bonds. And so that means they share the pair of electrons in between the two atoms. However, the carbon has a very significant partial negative charge. And in many ways, it is the carbon acts like it has a full -1 charge. Even though it's not technically a full -1 charge, it acts kind of like that. So this is how we think of these reagents, as having a carbanion where we have a full negative charge on the carbon, even though it's somewhat less than a full -1 charge. So these are all considered very reactive, and there are some precautions that we have to take when we're working with them. If we don't take those precautions, we'll end up messing up our reactants, and we won't be able to do our intended reaction. So how do we prepare these organometallic reagents? Well, for the organolithium reagent, it's pretty easy. And for the Grignard reagent, it's pretty easy. We typically prepare them by taking an alkyl halide and putting the metal in with that alkyl halide. So for example, with the alkyl halide, if we put 2 equivalents of lithium in, we will get the organolithium reagent and the lithium halide. Here is a more specific example. We've got bromomethane or methyl bromide, depending on how you want to call it. And when we put that in with 2 equivalents of lithium, we'll get our methyl lithium, which is our organometallic reagent that we can use. And we'll also get lithium bromide. And so that is the exchange reaction that goes on with that. For the Grignard reagent, we simply put the metal in, and we can think of it as that the magnesium inserts itself in between the carbon and the halogen. And that is sort of what happens, but that's the easy enough way to think about it. So that's how we're going to think about it. So the magnesium will insert itself into that bond, and we now get an alkyl magnesium bond, and we also get a bond between the magnesium and the halogen. Now you'll notice here that we typically will do this in ether, either diethyl ether or THF is another possibility, tetrahydrofuran, which we've talked about before. If you're not familiar with what THF is, go Google THF. All right. And now that you've Googled THF, you'll see that it's very similar to diethyl ether, except it's in a ring and it's a little bit more polar. So here is methyl bromide. When we put the methyl bromide in with the magnesium, we'll form the methyl Grignard reagent. And again, we need that ether there as a stabilizing agent. All right, here I'm going to talk very briefly about how the ether actually helps to stabilize the Grignard. So we usually use diethyl ether, and as I mentioned, you can use other reagents like THF, but diethyl ether is a solid go-to reagent for this. What happens, because the magnesium bears a significant partial positive charge, we can help to stabilize that by having the ether, the lone pair electrons on the oxygen, on the ether, act as a Lewis base to donate some electron density to that magnesium, helping to stabilize it. That just makes it so that it's a little easier to work with. All right. How do we prepare the organocuprates? Well, the way that we prepare organocuprates is we start with an organolithium reagent. So we take the organolithium reagent and treat it with copper 1 iodide, and that will give us the organocuprates. You'll notice that it takes 2 equivalents of our organolithium reagent, 1 equivalent of the copper 1 iodide, to give us the organocuprate. And when it comes to using this, we'll only be able to use one of those R groups as a nucleophile. So that's something to keep in mind later when we're doing these reactions. So here's a more specific example, methyl lithium plus the copper 1 iodide. We end up with the lithium dimethyl cuprate. All right, so our organocuprate, and then there is our lithium iodide as a byproduct. Now, there are other possibilities that we can use for organometallic reagents, and one that is quite common, and so I'm going to mention it here, are when we make the acetylide anion. And so acetylide anions are technically organometallic reagents. The one that we've seen before, if we treat a terminal alkyne with sodium amide or sodium amide, depending on how you want to pronounce that, if you treat that with that, then you will deprotonate this, and you will get the acetylide anion with the sodium and ammonia. Because and so this we can refer to as an organosodium reagent, but it's also a little bit different because this technically is not a covalent bond. This one we can think of more as an ionic bond, and that's because the sodium is bigger, and for various reasons it's less electropositive or more electropositive, and we can form ions with it instead of forming these covalent bonds. Regardless of that, this is an organosodium reagent, or we can just call it acetylide. Now, if you want to make the lithium acetylide, you can do that, but you'll need to start with a different organolithium reagent and acetylene. So if you want to form the lithium acetylide, you can do an acid-base reaction between the very strong base of lithium, methyl lithium as an example, although you can choose other lithium reagents. So methyl lithium, you can deprotonate that terminal alkyne, and that will give you the lithium acetylide. Here you'll notice that we put a covalent bond, and that's just because technically it is a covalent bond. It is less polar than the sodium carbon bond that we saw on the previous page, and that sodium carbon bond was so polar that we think of it as ionic. The driving force for this is that the methyl lithium is a much stronger base, or you can think of this this terminal alkyne as a much stronger acid than the conjugate acid of this base. And so just remember back to when we talked about acids and bases, the equilibrium will lie opposite the side of the stronger acid. And so that's what's happening here. Now, this is a reaction that can occur, and typically we don't want this to occur. And so I offer this as a precautionary note. We want to usually avoid reacting our organometallic reagents with alcohols and waters and amines and things like that. But it can happen. And the reason it can happen is because our organolithium reagents, in addition to being very good nucleophiles, are also very strong bases. So here we've got the methyl lithium. Methyl lithium in the presence of water, which has a pKa close to 16 here. We'll deprotonate that water. We'll end up with methane, which has a pKa somewhere at around 50, and we'll get lithium hydroxide. Well, this reaction, it's definitely irreversible. Once you've done it, you are not getting this back. And so, as I mentioned, typically that's not what we're trying to do. There are some special use case scenarios, which I'll talk about in a minute, where you might want to do this, but most of the time we're trying to avoid it. We have a similar problem when, if instead of water, if we have an alcohol present with our organometallic reagent. Here's a Grignard with water, and we'll protonate that Grignard, and once that happens, it's done. That Grignard is no longer going to go back to being a Grignard. Here we've got the propylithium, and our acid here is actually a more significant acid, this carboxylic acid. And so we'll deprotonate that, and we'll end up getting a protonated propyl group, which is just propane. As I mentioned, we generally want to avoid this, but there are certain cases where we might want to do this. All right, so let's say we've got an alkyl halide of some sort. That alkyl halide, we can use the metal to convert it into the organometallic reagent. And then we can convert that organometallic reagent into a hydride. In other words, we can replace the halogen with a hydrogen. All right, so the main use of our organometallic reagents is that they are very strong nucleophiles, and we're going to use them as nucleophiles 99.9% of the time. But there are certain situations where you may have a halogen that you want to get rid of, and in doing so, you can replace it with a hydrogen using these kinds of reactions. Now, most of the time, as I mentioned, we're not interested in doing that. We're interested in forming carbon-carbon bonds, and so we want to avoid getting the water in there. And I mention this because if there is water present when you attempt to form this, it will immediately react with your organometallic reagent and give you the hydrogen instead of having your carbon anion. So that's the reason I'm talking about this. But again, occasionally you might want to do this. So let's look at number 18. All right, so draw the product formed. This is really easy. We're going to replace whatever the organometallic reagent is when we treat it with water. We're going to replace whatever that metal is with hydrogen. So this becomes just cyclohexane. All right, so that's a really easy one. This is just going to become isobutane. There'll be a hydrogen there. I'll put the hydrogen for emphasis on that one. This one, when we treat it with water, it's just going to become toluene. All right, and then this one, we're just going to get that terminal alkyne. So 1, 2, 3, 4. We'll just get that terminal alkyne. So there's a CH on the end here. All right. Again, the main reason I show you these reactions, we don't typically use these in synthesis. We typically use these to warn against side reactions that we don't want. So again, all of these are with H2O. Now, here's what we're really going for. When we take some of these organometallic reagents and react them with carbonyls, we'll get some reactions that are very interesting. So we can react the organometallic reagents with aldehydes and ketones, and when we do that, we can get an alcohol. Now, what kind of alcohol depends on what kind of carbonyl compound we talked about. And in a little bit, I'm going to show you a slide where if we have formaldehyde here, we get a primary alcohol. If we have an aldehyde, we'll get a secondary alcohol. And if we use a ketone, we'll get a tertiary alcohol. I'll show you that again, and I'll mention this, that I just mentioned it. I'll go over that again, but that is one kind of reaction that we're interested in. If we have carboxylic acid derivatives, and the carboxylic acid derivatives that we're specifically interested in this chapter are the acid chlorides and the esters. With acid chlorides and esters, we can react with our organometallic reagent. So when we do this reaction with an acid chloride or an ester, with our organometallic reagent, we can get either a ketone or a tertiary alcohol. I'll go through how this happens in a minute. Getting the ketone, you need to use a specific organometallic reagent to do that. To get the alcohol, you use the other reagents. So I'll show you how it is we get that here in just a bit. The other possibility with these is that because these are such good nucleophiles, they can react with other things that are electrophilic. And later in this chapter, we'll go over this, where we look at reacting these organometallic reagents with carbon dioxide to give carboxylic acids, or reacting them with epoxides to add 2 carbons to our alkyl group here, and at the end have an alcohol. So there are multiple possibilities there. So this is sort of a preview of the next several sections in this chapter. So let's start with reactions between these organometallic reagents and aldehydes or ketones. If we treat an aldehyde or ketone with either the organolithium reagent or the Grignard reagent, and then follow it up with water, we can form a new carbon-carbon bond, and we'll also get an alcohol. So in a first step, and I want to distinguish that this is done first, and then we add water. If the water is there, then we go back to that reaction that we were just looking at a little bit ago, where we end up getting hydrogen in place of the halogen that we originally started with. So that's usually not what we want. But if we do this sequentially, in the first step, we treat it with this. In the second step, we protonate it. We'll get either a primary, secondary, or tertiary alcohol. And so this is a nucleophilic addition. So we are going to look at the mechanism of this. It's a nucleophilic addition, much like what we saw earlier. We're going to add the alkyl group and hydrogen across the carbon-oxygen double bond. So the carbon goes to the carbonyl carbon, and the hydrogen ends up on that carbonyl oxygen. So let's look at the mechanism. The mechanism involves 2 steps. First step is that our organometallic reagent, either organolithium or Grignard, reacts with our carbonyl to give us a new carbon-carbon bond. That gives us this intermediate, which is sort of indefinitely stable. We can form this intermediate for long periods of time, and it will stay like that until we add water. So we will have this alkoxide as our intermediate, and then when we add water, it will protonate it, and we will get that tertiary alcohol. Now notice on this, I'm using the Grignard reagent. However, we could do the same thing with an organolithium reagent, and we will get essentially the same reaction occurring. All right, we can also do this with the acetylide anion. If we do this with an organocuprate, it's not going to work, and I'll explain why it doesn't work in just a little bit. So our products of nucleophilic addition with either an organolithium reagent or a Grignard reagent is going to depend on what the identity of the carbonyl compound was to begin with. If we start with formaldehyde as our carbonyl compound, then our product is going to be a primary alcohol. If we start with a regular aldehyde, where one of these is an R group and one of them is hydrogen, then our product is going to be a secondary alcohol. And if we use a ketone as our carbonyl compound, and we treat that with an organolithium or a Grignard reagent, then we're going to get a tertiary alcohol. So I want you to kind of put this on your list of different reactions that you can use to form alcohols. And if you want to form a primary alcohol, you can do it with the formaldehyde, secondary with the aldehyde, and tertiary with a ketone. And so this is kind of a summary of that process. So formaldehyde gives us a primary alcohol. In this case, it gives us ethanol, which this is probably the least efficient way to make ethanol, but that's okay. Here we've got benzaldehyde, and so that's a regular aldehyde. It's got an R group here. We treat it with this ethyl lithium reagent, and it gives us this secondary alcohol. And then if we treat the cyclohexanone with this acetylide, lithium acetylide, we will end up getting this tertiary alcohol. So let's look at number 19, and we're going to draw the products of some of these organometallic reactions here. So here we've got a ketone and organolithium reagent. Because this is a ketone, that means we're going to get a tertiary alcohol. So we're going to add 1, 2, 3 carbons to that. So I'm going to go ahead and draw 1, 2, 3, 4, 5. So we've got those 5 carbons, and we'll get an OH group and a propyl group on there. And that will be our product after protonation. Here we have formaldehyde, and with formaldehyde and an organolithium reagent, we're going to get a primary alcohol. We will get that primary alcohol. This carbon was the carbon that was in formaldehyde. These 2 hydrogens are the hydrogens that are on that CH2. And then this oxygen is that oxygen that was in formaldehyde. All right, here we've got a ketone and our organolithium reagent. That's going to give us a tertiary alcohol. So probably the easiest way to draw this would be, I'm going to draw it like this. All right, so I've got that part of the compound. We do have an OH that is there. And then we have this phenyl group, which I am just going to draw as C6H5, but it is a phenyl group. And then the water is just to protonate, so we get the alcohol. All right, finally, on this one here, we've got this long part of the reagent and then formaldehyde. With formaldehyde, all we're going to do is add CH2OH, the water to protonate it to give it the OH. And so we're just going to add CH2OH to the end of this. Put that double bond in there. Put this triple bond All right, and just to be clear, just so we can count these out, so everybody knows. So one, I'm gonna count from this side. 1, 2, 3, 4, 5, 6, 7. There's 7 carbons in this. Well, 8 if you count that. So 7 carbons in the main chain here. And when we count 1, 2, 3, 4, 5, 6, 7, 8. We've added 1 additional carbon to this and the OH at the end. So here is an example of using this particular type of reagent in a synthesis. So here we've got a steroid backbone, and I don't know exactly what compound this is, but it's a precursor to making this synthetic hormone over here. And so when we do this reaction, we treat this carbonyl with this lithium acetylide. It comes in, reacts with that, and then the second one protonates to give us the alcohol. And we have this precursor, and then one step, which is just going to be the deprotection of this. We're going to talk about protecting groups a little bit later in just a couple of sections here, but we deprotect this to give us the alcohol. And this is the ethynyl estradiol, which is used as a synthetic hormone in birth control pills and other applications in which that hormone can be useful. So a very, very useful medicine, typically used in combination with other drugs for a complete drug. All right, so now let's look at doing retrosynthesis with Grignard reactions. And again, retrosynthesis is where we think backwards. So we start with our product, and where do we break the bonds to get our starting materials? So there's 2 steps really that we can use. First, find the carbon that's bonded to the hydroxyl group and see what other carbons are attached to it. So here's the carbon that is bonded to a hydroxyl group, and you'll notice that we've got 3 alkyl groups. There's 2 methyls here, and whatever this R is. Well, then we just select one of those bonds, and in this case, we're selecting the R group, and that's the bond we're going to break, is this red one here. And so wherever the alcohol is, that's going to be our carbonyl compound, and whatever this other side is, that is going to be our organometallic reagent, and in this case, a Grignard. Although it could have been an organolithium reagent, that would have worked fine as well. So that would be our 2 starting materials to make this. So let's look at a specific example of this. So here is the pentan 3-ol, the compound we're trying to make. So with pentan 3-ol, we've got 2 different carbon groups that are attached to the carbon that has the OH. They are both ethyl, so it doesn't matter which one we pick. So we're going to arbitrarily pick this one as the new bond that was formed, which means this side that doesn't have the OH, that's going to be our Grignard. Again, could be an organolithium reagent. So that's going to be our Grignard. And then this side that has the OH, that's going to be our carbonyl compound, which, because this was a secondary alcohol, this was an aldehyde. If this had been a tertiary alcohol, this would have been a ketone over here. So now if we turn that reaction around, so here we've got the aldehyde. When we treat that with our organometallic reagent, either Grignard or methyl, or the ethyl lithium would work here. We treat it with that organometallic reagent, and then we'll get this as an intermediate. This alkoxide is an intermediate, which we protonate with water in a second step, and we will get our alcohol. Now, I'm going to point this out because on some of these problems we're going to do, there's more than one way to get a final product. So there's more than one way to synthesize either a secondary or, in the case we're going to look at, tertiary alcohols using our Grignard. And so we're going to look at all of those options for the one that is on this problem, number 57. All right, so what Grignard reagent and aldehyde or ketone are needed to prepare each of these alcohols? And we want to show all the possibilities. So for this one, there's two possibilities. We could cut it here and that make that our organolithium and this our aldehyde, or we could cut it here and make that our organometallic reagent and this our aldehyde. And it just depends on which way you want to do it. I'm going to do both ways. So I'm going to start with this one. So 1, 2, 3. I want to do that in dark. 1, 2, 3. All right, so we've got that aldehyde. And so here, that's that aldehyde, 1, 2, 3. And then we're going to use this organometallic reagent, which is a propyl. So 1, 2, 3. MgBr. That is going to be step 1. So we can get rid of that plus there. And in step 2, we'll use water, and that will give us this product. So again, this part is this aldehyde, and this part is that organometallic reagent. If we did the other one where we made this our organometallic reagent and this our aldehyde, now we would start with a 4-carbon aldehyde. And in step 1, we could add a methyl Grignard, and step 2, we could add water, and we would get that same product. Now, which one's better? I don't know. I don't know. It may just depend on which one you have the ingredients for. So which one you have your starting materials for. All right, this next one, there are 3 possibilities. Since this is a tertiary alcohol, that means that we're going to use an organometallic reagent and a ketone to make this. And as I mentioned, there's 3 possibilities. So we can make this our organometallic reagent. We can have this methyl as our organometallic reagent, or we can have this cyclohexyl as our organometallic reagent. All right, so let's do the ethyl first. So we've got that cyclohexyl, got our ketone. And then if we're going to use the ethyl, then we just need a methyl there, so CH3 there. We treat that with the ethyl Grignard in step 1. In step 2, we'll use water. And that will give us this particular product, which I'm going to draw my way, and all right, that's the same thing as that. All right, so another possibility here, another possibility is if we had cut here, all right, so we have 1, 2, so 1, 2, 3, 1, 2, 3, and then here we're going to use CH3, MgBr, and H2O, and then that would give us this same product. So here we're using the methyl. And then finally, we're going to use cyclohexyl as our organometallic reagent. All right, so here we've got the 4-carbon chain that is this ketone. And in step 1, this one gets a little trickier to draw, MgBr, and in step 2, H2O. And it will also give us that same exact product. All right, any of these will work. So any of those will work. If I were going to pick one, I'd probably pick one of the first 2 because it's going to be easier to either make these Grignard reagents or buy them. whereas with this one, it'd be a little more challenging. That said, when it comes to the ketones, this would be the easiest ketone to make. So I think it just depends on what you're going to do. All right, for this last one, we also have a tertiary alcohol. However, and so we're going to need a ketone and some carbonyl compound. However, it's probably not going to be viable to do an intramolecular, because we're making a ring here, to do an intramolecular Grignard reaction. So we're just going to do the one where we break this. So our carbonyl compound will be cyclohexanone, and this will be our Grignard. Well, make sure I'm still on the page. I am. So step 1, we'll use the ethyl Grignard MgBr. Step 2, water, and that will give us that product. We'll get OH there, and that ethyl group there. All right, so there's different ways, and like I said, doing an intramolecular Grignard is very tricky because you have to form the Grignard and then do the intramolecular Grignard all in the same pot at the same time. It's a little tricky, so I would avoid doing that. I would use the other one. Cyclohexanone, easily available. This is easily available, so that's an easy one to do. So in this section, we want to talk about protecting groups. And this is just going to be the first of many protecting groups that we will see in this text. So we can use organometallic reagents with a lot of different kinds of things, but we're going to find that there are certain things like NH groups and OH groups that will be deprotonated by our Grignard reagent. And as a consequence, it makes it not viable to do the synthesis, a Grignard synthesis, with that functional group present, unless we use protecting groups. So here is an example. We've got this 5-hydroxy-pentane-2-one. And so here we've got the carbonyl that we want to do the Grignard on. Our idea is that the Grignard is going to come in, react with that, will protonate, and we'll end up with this tertiary alcohol with that primary alcohol on the end. However, when we do this, that Grignard is going to come in, react with the OH group. It'll deprotonate. We'll have methane. That methane is gone forever. We will not be able to use it as a Grignard anymore. There's no recovering it, and we will get this alkoxide. And that alkoxide is not going to do the reaction that we intended. So this doesn't give us the product that we want. So we really can't have the NH or OH bonds present on something that we're using a Grignard on. And again, every time I say the word Grignard, we can also substitute in there an organolithium reagent. So how do we get around this? Well, like I said, we use protecting groups. So there's a strategy for doing protecting groups. The strategy is very simple. First, protect. So we convert that OH group into something else that is unreactive in the particular reaction that we're going to be doing. So we're going to protect it. We call this the act of protection. So we're going to put a new blocking group in that's called protection. Then second, we're going to carry out our desired reaction. And then third, we're going to remove the protecting group, and we call that deprotection. For alcohols, a very commonly used, this is just one of many, a very commonly used protecting group is called a Silyl ether. And there are a couple that are available, but the favorite for most organic synthesis people are going to be, so for organosynthetic chemists, we have that name, right? So for organic synthetic chemists, we like to use Silyl ethers. And the one that we like to use is called tert-butyl dimethyl silyl ether. What's great about tert-butyl dimethyl silyl ether and other silyl ethers, just to be specific, what's great about this is that these are not very reactive with either acid or base. So you can put this in a fairly strong acidic solution, nothing happens to it. You can put it in a fairly strong basic solution, nothing happens to it. In the conditions of doing a Grignard reaction or some sort of nucleophilic addition or substitution, which we're going to talk about a little bit later, these Silyl ethers are essentially inert. They don't react. And also, this is a key requirement, it's fairly easy to remove that Silyl ether to return it back to the alcohol. So let me show you how it works. So to prepare the tert-butyl dimethyl Silyl ether from an alcohol, we're going to use tert-butyl dimethyl Silyl chloride and an amine base, which is a fairly mild base called imidazole. So here I've got a little picture of imidazole up here in the corner for your convenience, so you know what it looks like. But here's our alcohol, and again, many alcohols will work here. There is our TBDMS chloride, tert-butyl dimethyl Silyl chloride. And in the presence of this fairly weak base, we can deprotonate this OH, and this will react with the silicon to make a silicon-oxygen bond, and chloride will be lost. And that is our protecting group. As I mentioned, that protecting group is pretty robust and will stand up to a lot of acidic conditions and basic conditions. And so we can do all kinds of reactions on it. And then when we're done doing those other reactions, we can use a deprotecting agent. And in this case, tetrabutyl ammonium fluoride. So 4 butyls on an ammonium, on a nitrogen to make a quaternary ammonium ion. And then fluoride as our counter ion. All right, and that fluoride is really good at reacting with silicon. It just so happens that the silicon fluorine bond has a strength up there around 500, I forget the exact number, about 580 kilojoules per mole. Much stronger than just about any other single bond that we've talked about before. So it's such a strong bond that it makes it possible to remove that silicon from the oxygen, and in the process of doing this, we protonate the alcohol and we return to our alcohol. So let's look at how this works. So how do we use these Silyl ethers? So to use the tert-butyl dimethyl Silyl ether, we will take our compound that has an alcohol. There's our ketone that we want to react with a little bit later. We're going to use the tert-butyl dimethyl Silyl chloride plus the imidazole. That will produce this protected alcohol, which we then can use our Grignard or other organolithium reagent or something like that on there. But our Grignard reagent, which will come in and react with that, protonate it with water. And then we've got this it's still protected. We have produced our alcohol, but this is still protected. So now we need to put in the tert-butyl ammonium fluoride, and that tert-butyl ammonium fluoride cleaves that oxygen-silicon bond, and we protonate the oxygen to give this OH. So we have now generated the compound that we wanted. This would have been impossible to go directly from here to here, but because of our protecting group chemistry, we can do this. This is a very important concept. Anybody who does any sort of serious organic synthesis ends up doing this. So protecting group chemistry is a big deal. So let's look at number 24 on the in-class assignment. Now, I've already gone through and drawn the compounds that are in between. So how can we use a tert-butyl dimethyl Silyl ether to protect this? So on this, we will do the TBDMS chloride to protect that alcohol. And then we also need the imidazole. All right, so there's our imidazole, and that will give us this protected ether. So now we've protected that group. We're ready to do the reaction to form our ethynyl estradiol, which is that hormone I was talking to you guys earlier about. We're going to use an organometallic acetylide ion, and I don't know that it really matters. I'm going to use the lithium one, so the H, carbon, triple bond, carbon, lithium. And in a second reagent, our second reaction subsequent, we're going to add water to protonate to give us the alcohol. And then finally, to go from this, which still has our protecting group here, to our unprotected final compound, we will use the tert-butyl ammonium fluoride. So tert-butyl ammonium fluoride, and that will give us that particular compound. All right, well, I'm going to stop this video here. We're at 51 minutes, and I like to keep these at an hour or less. So I'm going to stop this video here, and we'll continue on the next section in what I think will be our final video for this chapter.